Good morning, everyone, and this is the more technical session of the CNPS Saturday morning chats. And our usual host, Ian Cowan, he's actually going to be presenting today on longitudinal electrodynamic radiation in vehicle range detection and ranging, which is a little bit of a different topic for us. So I think we're just going to go ahead and Ian, take it away.
Well, thank you, everybody. And I must first apologize. Franklin, I think, was too polite to mention it even, but I lost my voice last week. So I normally don't speak like this. But I think if I speak in low frequency tones, it's reasonably understandable. And I think the recording will be all right. So you'll just excuse me. Now, so Franklin has already told you. I'm going to have to share my screen now to get my slides up. So let's say present. Present maybe slides. Let's see what happens. No, there's no slides. Your computer. File. We should get this up in a moment now. Is this occurring now? I'm not sure if it's coming up now. Processing. Add to stream. Let me see now. Can I sometimes there's better actually if I go into that. I think I can get it bigger now if I sorry for this messing around, but we just try to get it better than that. If I say share my screen, this is better, I think. Now what we'll do here is we'll can everybody see that? Well, I can't hear you, so I just have to put it down for a second just to check. And maybe share. For Franklin, could you see that when I put the thing up?
Yes.
Okay. No, but could you see the very big one?
Well, it already looks big. I mean, in fact, I'm a little surprised that it's full screen for us right now.
Is it? Oh, okay.
With just you and me in the corner. So.
Okay. Well, then I'll proceed. Okay. Well, as was announced in the introduction by Franklin, we're talking about a longitudinal electrodynamic radiation. Now, this is something which is rather heterodox in that electromagnetic radiation is considered transverse, and we'll discuss that in a minute, with the electric and magnetic fields being at right angles. Now, there is a very small amount of dissident work done on longitudinal radiation. Sometimes it's called longitudinal electromagnetic radiation, but I prefer the term electrodynamic radiation because it isn't really based on the magnetic vector. It's really just the electric vector, which is moving in the same direction as the energy flow, or the sort of pointing vector. Now, what I'll be doing here is, and you'll excuse me if I just take water now and again. 2 or 3 years ago, I was involved with Dr. Allen and some other people that I'll be referring to shortly in a project to make use of longitudinal electrodynamic radiation in vehicle detection and ranging. And it was with actually his son, I think, was working in this area in one of the transport authorities and so on. So I'll be talking about that, but I have permission just to give an indication of what we had intended to do, because we went quite far in the concept of this, but unfortunately we ran into some difficulties. Some people had to leave and so on. So we'd be very happy if others would sort of take the mantle and use the preliminary results we had. So I have permission to do that from Dr. Allen. Now, okay. So, well, this is basically what I think I was intimating. Normal electromagnetic radiation, what we normally conceive of, which is used in detection and ranging. Well, I suppose we're talking about things like radar, or generally in transmission and reception via Hertzian waves, is always transverse. We have the electric field intensity E, the magnetic field intensity H, and the pointing vector, the transference of energy per unit time per unit area, is the cross product of those two vectors, but they're all mutually perpendicular. Now, so I'll be talking initially about the theoretical basis for electrodynamic longitudinal radiation, and this is posited on the general solution to the inhomogeneous wave equations, which admits also of longitudinal electric waves where E and S are in the same direction. And longitudinal waves are determined by the scalar potential rather than the vector potential, the scalar potential. So they are sometimes referred to as scalar waves, though I would caution you not to confuse this with Tesla's ground-hugging waves. So in a way, we're a bit like Nikola Tesla in that we're going forward past what is generally conceived, but it's not exactly the same as what he was doing with his big transmitter for the ground-hugging waves. Now, so reference publications. So we can come back to any of these, and of course, this will be recorded in real, immediately after the talk. It'll be available. But it's very important for me to highlight the work of J.P. Wesley, who was an American physicist who retired to Germany. He died a number of years ago, but he's written a book, Scientific Physics, which I think a number of us got actually through his widow, who's living in Germany. She's selling it privately, but it can be got if necessary. Now, he's also another book, which is a lot of it is common actually to scientific physics. He's written with one of our people who's participated actually in the CNPS work, Peter Marquardt, and the work is light, a photon flux. But actually, it's not only about light being a photon flux. It's about all Wesley's ideas, field theories, which can be applied to electrodynamics and can also be applied to gravitation, for example. Now, I'll be referring to one paper later on, which Wesley produced in cooperation with this gentleman, Christian Monstein. Well, this is where they did some experiments they gave the theory, which is similar to what I'll be doing, but then they detected these waves. They say observation of scalar longitudinal electrodynamic waves, EPL, and there's the reference. Now, for balance, I'm giving one more reference, which is slightly contradictory. So I think there's a USA, Butterworth et al. There are quite a number of these people, academics. Longitudinal electromagnetic waves with an interrogation mark thereafter. The Monstein-Wesley experiment reconstructed. Journal of Scientific Physics, blah, blah, blah. Now, they actually repeated Monstein and Wesley's experiments, and they seem to get very similar results. So one could say they did detect the waves. However, Butterworth et al. Strongly argue that there's no such thing as longitudinal electromagnetic waves. It's a false interpretation. So even though they got similar results to Monstein and Wesley, they have a completely different interpretation. And in fact, their views would be more mainstream. So either they're such distinguished academics that they're giving another view, hold back, don't run forward and to the conclusion that there's something else out there which hasn't been considered. Or some people might say, well, they're a bit influenced by orthodoxy and they don't want to move so far away. But I've given that reference anyway in Balance. Now, there's some references there which are just what we were doing. We said, well, look, we could apply it to it's some work which has been published actually by the IEEE on electrical architectures and power requirements for automated vehicles using electromagnetic radiation. And we were discussing with the prime man, actually, the prime practitioner. He's a theoretician as well, but the prime contractor, or the man who would do this for us. And what he's doing is, or he's been using the meridian of these highways for solar panels, but also for things like detection devices, sonar or radar detection devices. And you could use the median of those motorways to put this equipment down. And I've just got a reference there. It's California, Long Beach, USA, 2018. Also, Charles William Lucas, one of our regular participants here, he's written an interesting bit, and in fact he's put this in some other publications. What is the nature and cause of life? And he's given some reasons that one might conceive that these scalar waves are actually important as the essence of life, and they can be detected, and furthermore they could perhaps even be used to cure certain diseases. So I've given one of his references there in the Foundations of Science, which is this newsletter that they produce. And the other thing is there's one more sort of information on some equipment used for the 77 gigahertz radar transceiver using EM waves, and this is I think this is where Sean Allen, who's one of the sons of Dennis Allen, has been involved. But we'll come back to that later. So no, I don't know why I got Tony Grotz up. He's interested. I just clicked on him by accident. So we'll look at some of those comments later, no doubt, with Franklin. Now, I just wish to make a number of acknowledgements, insofar as my voice will allow me to do this. Well, first, Dr. Dennis P. Allen, Jr. from the USA, who's here with us today. I'm glad. And I've been encouraging Denny to chip in because actually he's the collaborator, but he's also the originator of many of the ideas. So I like to think that I'm an original thinker, and maybe I'm not trammeled by conventional views, but I think many of these views I wouldn't have come across without the promptings of Denny. And so he's the originator. I'm maybe building on some of these at the most. So he's the first there. Now, actually, Bob Gray, who's joined us as well today, well, we were looking, Denny and I, and we were just solving them and find the solution of the relevant partial differential equations. But Bob is a very precise mathematician, and he wrote a few pages of mathematics giving us the general solutions to these equations, and I sort of use those. So I'd like to acknowledge Bob's work there. Now, what I do is I'm obviously extremely interested in the mathematics, and I want to make sure that it's all correct, but I'm not going to put up 10 pages of mathematics here for all of you. I think that isn't appropriate for a talk like this. I'm interested in making sure that mathematics is there and is sound, but I adhere to the diktat or the advice of Polonius in Shakespeare's Hamlet in a case like this, that brevity is the soul of wit, and tediousness the limbs and outward flourishes. So in a talk like this, I'll be giving you the assumptions, just maybe a couple of lines of assumptions, what you use, and then the result. There might be just 3 lines, like a syllogism. Oh, these are the mathematical assumptions. This is what we used, and this is the result. If you want more information on the theoretical derivations, those can be given. The third person is the contractor, Dr. James Wolter, who I mentioned earlier. But he's actually got the benefit of being a theoretician who's qualified and he's done work, although he claims it's many years since he was fiddling around with all this complex mathematics, but he's conversant with it. He's no stranger to it, and he's been working in the USA in implementing many solar energy and transmission projects and so on. And I suppose Denny has known him for quite some time, and we purloined him into this project, and it was like a tripartite thing, and we were doing conference calls actually with him and so on. But I think I think his involvement has probably been terminated. Well, it was suspended because he had 1 or 2 health issues. Here's a man who can't speak talking about people with health issues. But anyway, but I think he's decided now to pull back in some of these works, because he wants to concentrate on 1 or 2 of his pet projects, which are maybe a lighting project or solar energy project, and we're not going to push him. So well, that's one of the reasons actually for today's talk, because not only do we want to share with all distant physics and anybody participating today the results that we obtained, but we want to encourage them to get involved and maybe take over some of the work that James Wolter might have been able to do. Now, Christian Monstein himself, who's he's in Switzerland. He's a member. He's working in astronomy now. He's a member of the Royal Astronomical Society, or maybe the Switzerland Society. He's a theoretician. He's totally au fait with Wesley's very theoretical work. But he's also an experimenter and an advisor. Now, his advice has been given without any qualms at all, and I want to mention that because any questions that we had to him, we just flipped to an email and we get an instant answer back telling us and advising us what to do and so on, because he had been successful in doing this work in Switzerland. I'll give more details about what he did and where he did it, but he did his preliminary training and he was at college in Germany. And although I haven't actually verified this directly, I take it that he's German, and he moved to Switzerland, sort of semi-retired, but he's very much involved into radio astronomy and so on. I just want to mention maybe delicately that Denny has informed me that he, in other words, Christian Monstein, got into some difficulty with some authorities in Germany. Now, I'm not quite sure who they are or why they might have been, but I think it even ended up in some legal matters. Now, I don't know if it's because he was a heretic and that he believed in longitudinal radiation, or he claimed he detected it, and it's in itself is enough for people to concentrate on you. But anyway, Denny said that he got into trouble and he was threatened by a German judge with consequences up to and including imprisonment. So maybe he thought it was getting a bit too hot for him. I don't know. But anyway, Christian has been very forthcoming in his advice, very polite, a thorough gentleman. And last but not least, Mr. Sean Allen, who's Denny's son, who works in the, if any of this has been updated by them in the last 2 years, Denny will come in and chip in. But he was working for the Michigan Department of Transport, and he's an engineer. And actually, he was very forthcoming in telling us what exactly he's doing, and very open-minded in regard to looking at the possibilities of our filling the gap with this new type of technology. But he'd always say, look, I'm not an electronics engineer. This is beyond me. I'm not a mathematician. He was always very, very humble, but he was very useful in giving us guidance in how this might work out. Okay, now, okay, I'll just I'm just going to because Nick has just sent me a nice note, so I'll just reply to it there. Okay, now a lot of preliminary stuff. Oh, I'll frighten you now. Okay, so let's just do a very brief summary of the existence of vector and scalar potentials. So the vector potential, which is normally given the symbol A, and in the excuse me, in the Wesley theory, this really is more fundamental than the magnetic field intensity or the magnetic induction, which is the curl of that. So A can be expressed as a function of the radius vector, like the position r and time t, as mu naught over 4 pi, just the magnetic permeability, the volume integral of the current density. Now we're talking about at any point r, where the the origin of say the current density is r dash. So you just integrate that with regard to the distance between them, and you get that volume integral. But the analogous thing is maybe the more common scalar potential, which sometimes is called V because it gives rise to voltage, but we'll call it phi here, phi of RT, 1 over 4 pi epsilon naught. So I'm using the SI units here. Actually, just another thing, caution maybe. Wesley uses the CGS units, which actually in a way are more fundamental. In my first year physics, we studied the CGS units because I think they said at the time it was more fundamental to have all these 4 pi terms in. But anyway, later on when we got to be using more practical equipment, the SI units shone out, and they were obvious that you had things like 4 pi coming into spherical geometry, but you didn't have it coming into plates. So anyway, so we're using the rationalized SI system now. So we have 1 over 4 pi epsilon naught instead of just say K, the dielectric constant. And their rho is the the charge density. So again, it's a volume integral, and same thing at any point r dash and t dash we're evaluating it. Now, using the definition of B, that it's the curl of A, and also the general definition of E, the electric field intensity, as minus the gradient of the potential phi plus, well, it's minus, it'd be minus there in the bracket, the partial differential of A, the vector potential, with respect to T. And we also use the Lorentz gauge, which is that the divergence of A plus epsilon naught mu naught, the partial differential of delta phi by delta t equals naught. Now, and just in one word, I'll try to be very, very brief about the Lorentz gauge. Insofar as I can see it, there is a preponderance of equations here, given the number of variables. So we can assume various gauges here. But actually, the Lorentz gauge, by the way, I should mention here, that isn't a misprint. There's no T there. And I've discovered, even in quite respectable electromagnetic texts, they mix him up with Hendrik Lorentz, who's responsible for the Lorentz transformation and a lot of work in electromagnetic radiation. There's another gentleman altogether, not a Dutchman, he's a Dane, Lorentz, it's pronounced the same way, I suppose, Lorentz, but it doesn't have the T in it. So it's yeah, I'm just trying to think of his first name, just lost it a second. It's Ludwig Lorentz. So he introduced this. He was a contemporary of Lorentz's, actually, and that's why they're frequently confused. So just a comment on that. But this is actually analogous to the continuity equation in fluid mechanics. So it's an obvious relationship between, you'd imagine there's some relationship between the two because they're formed, but there's an obvious relationship. So using that, we can actually derive inhomogeneous wave equations for both phi and a of that nature. So, the very common equations for E and H are replaced in this case by the common wave equations for phi and a, but they're inhomogeneous. There's not zero here. There's a rho over epsilon naught and there's a mu naught j here. So unfortunately, this moved a bit. I don't know how it did that. Maybe just the way I'm projecting it. But the solution of the vector potential wave equation. This is an interesting point actually. So I'll just I think I'll just have a look at the original slide on my screen here so I get it right. The solution of the vector potential wave equation subject to conservation of power density. Now, the conservation of the power density would mean that the sum of the divergence of the Poynting vector S and the rate of change of energy density D. Okay, so that's what I just wanted to get up. Well, that gives transverse electromagnetic waves where S is actually the Poynting vector and D, the energy density, is that. Now, actually, this is really fairly familiar because this is the normal case, the vector potential. And, if you consider that curl A is B over mu naught is H, and that's E. So that's just as S is equal to minus E times A, the cross product of E and H. Not the minus that comes into the E there. And simply the D is it's the normal expression, it's a half of the E squared epsilon naught plus half of H squared. You see that's because the B over mu naught is it's a half of mu naught, I think, H squared. It's the normal expression for the energy density, and you get this sort of a thing here where you have the E there and you have the H there, the B there, and so on. Okay, all very well. It looks a bit more complicated than it need be, but in actual fact, it's what we're all familiar with. But what happens if we solve the scalar potential wave equation? We've just solved the vector potential wave equation. I had two equations there. What happens if we solve the scalar potential wave equation with similar restriction on energy conservation? In other words, that the rate of change of energy conservation given by the divergence of the Poynting vector plus the rate of change of the energy density and so on equals zero. Well, what happens? And the late Murray Gell-Mann said everything which is not forbidden is compulsory. Well, he was talking about another area altogether, about the preponderance of subatomic particles. But anyway, the thing applies that if it's not forbidden, let's do it. And if we do that and do the maths, we get longitudinal electric waves with Poynting vector S and energy density T, the following. So you can see the Poynting vector doesn't have any magnetic component. It's just an electric component. And similarly for the energy density. So one is less familiar with those because that wouldn't even be in the textbooks. It wouldn't say, look, you can do that, and that's false. It doesn't. Sorry, I've gone too far. It doesn't exist. They would just say that's rubbish. Don't do that. It's prohibited. But if you do that, you get this a longitudinal wave here with compression, rarefaction, the wavelength, and so on. So that's a theory as to why it could exist, or one might even go further and say it must exist. But you can take your choice in regard to that. If we just accept this provisionally, we can get the general form where the net Poynting vector we call S sub n, and the net energy density would be D sub n. Okay. Well, then we put it all together, and I've just added them up. We just add the two together, The red would be the transverse part, which, as I say, if you use the definitions, we're all familiar with it, occurs in all the textbooks. And the green is the longitudinal part, which is in a different form in Wesley's books, because he's using the CGS units, but it's basically the same. He's using the same equations and the same assumptions. And Monstein, then he's using both, actually, depending on which paper you're using. For the practical experiments, he's like us, using SI units, but I think in the earlier work he's with Wesley. Okay, so yeah, I know. My eye has just hit on Franklin's point. Why do we need such complex wave equations? Shouldn't it just be W equal cos t? Well, yeah, I mean, to a certain extent that's true. But remember, the solution would be more like something like twice pi into sine or cos t, small t over large T, which is the period, minus x over lambda. So there's a spatial change plus a time change. Yeah, I'm giving good advice by a gentleman here, much appreciated, on laryngitis. I've been thinking of trying things like Vicks nasal spray. He said that, but because I was telling people I tried one or two things, lozenges, and they seem to make matters worse. So, but anyway, thanks for it's a viral thing. I think, by the way, in some cases it can be bacterial, but in most cases, like a common cold. I might have picked it up, I don't know, just last week. So anyway, I actually had it in 1987 before. So as far as I'm concerned, if I only get it once every 36 years, I can take it. Okay. Okay. Right. So there's a theory. I don't think I'll be going very much more into theory, except to say that obviously there are pages and pages of mathematics behind this, just to derive it. But I've given you the bones as to how to derive it in as brief a period as possible. Now, Monstein and Wesley, before he died, did this experiment in Senval in Switzerland, basically on the Rhine River. And they built these aerials or antennae, transmission and reception. Now, one was 4 meters above ground level. There was 4.4 meters. They give all the details in the paper, which I referred to. But basically, it's a spherical ball. I think they were using aluminium in the first place. Now, the basic point is that transverse radiation is not produced by spherical ball antenna because of the symmetry. And this is basically what we call the hairy ball theorem, which basically would indicate that you need like a parting in your hair, a discontinuity. But if you don't have that, if it's all symmetrical, everything cancels out, east to west cancels out, and so on, and you would not get transverse radiation produced. But what they did is they fed a coaxial cable to the center, which delivers and takes away the signal respectively in the transmitter and receiver. The core would be connected to the ball, and the shield would be earthed. So that's the protection there. Now, so this is what they did. Now, they got radiation, but how do we know that it's longitudinal? Well, what they did is they had a rotatable table with a cubic array polarizer analyzer with half wavelength rods. So in other words, the dimension of the rods would be lambda over 2. And what they did here, I'll just get up my larger one so I can read it better. Yeah. So what they say is the rotatable 3x3 polarizers on top of a wooden chair with lambda over 2 rods made of brass. The polarizer can either be turned by hand or, by the help of a disc record player. So this is this thing here. But this is graphing the normalized power transmission 1 max against deflection angle. So the measured transmission T, which is this thing here, these dots actually, for longitudinal waves at 433.59 megahertz, passing through the polarizer analyzer shown in figure 2 as a function of the polarizer angle phi between the direction of the wires and the direction of propagation. The solid curve represents the theory that they worked out this theory x of minus 4.4 cos squared phi, which is pretty close. But but you can see that the deflection angle, when the deflection angle is 0, you're getting 0 transmission, and when the deflection angle is 90 degrees, plus or minus 90 degrees, you're getting maximum transmission. So that indicates that they're simply longitudinal waves. Well, to their satisfaction, because Butterworth et al. Contest that, but that's what they did. Now, so this is just a brief indication of what we did later on. M is Minnesota, I think, not ministry. Minnesota Department of Transport radar pilot, and this is some single ship equipment radar transmitter. The device can be intended for use in short, medium, long wave. So this is what they're doing, and these are the frequencies they're using. Radar transmitter, low power radar transmitter, which integrates 3 transmitters. So they've done a lot of work, and we thought that they could maybe modify the equipment to use longitudinal radiation generated by these type of antennae. Now, the long-term human exposure to transverse microwave radiation could have deleterious effects, or at least later claims of such effects. So maybe the latter is even more worrying, because once maybe the legal people got hold of this, you could have claims coming in 30 years' time that, oh, you wrecked my husband or my son or something. But the longitudinal radiation produces no such harmful effects, and there's a lot of information available to that. And there's certainly a lack of information that there may be deleterious effects from longitudinal radiation. Well, of course, if it doesn't exist, I don't suppose it's doing any harm. But as I say, there are some indications that actually it has beneficent medical effects, that perhaps it might have accelerated the healing of broken bones, for example. There is some information on that. And Dr. Lucas has talked about that and some work that has been done in Europe, by in France in particular, by this. Okay. Right. So so that's what we were doing there. Now, we then got down to trying our hand at a practical design for such a transceiver, which we wanted to use for this experiment, for this project. Just a reminder that the general induction equation is the Wesley equation. The Faraday equation would be a special case of that, but the electric EMF would be composed of the negative, the Lenz law, it's in opposite direction, of the partial differential, time differential of the vector potential, this strange quantity, which is the v dot nabla times a, sorry, I'm going too fast, and the other one, a dot nabla times v, and this acceleration term, which would come in phi epsilon naught mu naught. So triple integration for copper spherical ball ball would actually give an inductance tens of atto henries. Atto would be 10 to the minus 18 of a henry. So it's very, very small, proportional to radius. So you get something like that, 100 millimeters to 2 meters. We made some approximations then, though, taking into account the cable which was going in the center. This is the self-inductance here. So using the expression for the capacitance and the inductance, that seems to be a semi-empirical equation for this type of thing. We found that at resonant operation, we say RR, this is the radius of the ball, which might be copper, I think, or it could be aluminium. I think we might have been using copper at this stage, but we got this expression related to the ratio of the speed of light to the frequency you were using, multiplied by this factor 0.11. We also got the resistance of it, the resistivity and that sort of thing. So we then plugged it into Monstein's and Wesley's frequency of 434 megahertz. We found that the resonant radius, if I may use such a term, was 79 millimeters. The capacitance was 8.4 picofarads, and the inductance would be 0.0015 microhenries. The resistance was 0.167 ohms. So we said, that's press. So we're on the way to giving Jim actual values that he could use in his setup. And we said signal of 434 megahertz to be fed to the core of coaxial cable in transmitter sheath is earthed. Now, I'm not sure if that frequency would be the most important, but I think I suggested that why not try to keep to the frequency that Monstein and West were using to try to duplicate what he was doing in the first instance. And if we find it's more convenient to use a different frequency, we'll do that. And Denny and Jim agreed to that. So I think that's really as far as we got, unfortunately. Yeah. So there are a lot of comments here about expansion of things like water and so on, but we let them carry on there. Okay. Right. Now, so in conclusion, theory has demonstrated how longitudinal or scalar, if you see those terms, they're interchangeable, electrodynamic radiation may be produced. So it's not prohibited by theory. In fact, I think Monstein and Wesley would say it has to be around because the theory says so. But I'd say it's not prohibited by theory. It's certainly quite possible that exists, and let's do some experiments to see, does it exist? Yes, this has been demonstrated experimentally by Monstein and Wesley, and I pointed this out as well. It's actually reproduced by Butterworth et al. Of Texas A&M University, Kingsville. And here I put it in italics because they counter the theory and the very existence of longitudinal electrodynamic waves. So, I mean, we all parody these philosopher priests who wouldn't look into Galileo's telescope because when he saw the moons of Jupiter, they said, well, they knew they couldn't exist, so we're not going to look into the tube. But this isn't the case. These people have repeated the experiment successfully. They haven't said, I won't even do the experiment. It's a waste of money because we know for certain that longitudinal electrodynamic waves don't exist. They said, no, open mind, we'll do it. And they found the same results. But then they give reasons as to why his interpretation is correct. And, I'm suppose many of us here would see some similarity, perhaps, not all of us, in the experiments which have been done with very precise equipment since the beginning of the 19th century in looking at, things like speed of light in different directions, and in particular things like non-inertial speed additions or subtractions. So in other words, things like maybe radar ranging of planets or maybe on a smaller scale, the same thing as the Sagnac effect. And the mainstream, have no problem in admitting, well, they don't say it's rubbish and whoever did it just made it up and won't even look at it. They say, oh, yeah, we've done it all. And they give somewhat strange reasons as to why SRT, for example, is still quite consistent with all that. Anyway, I just put that in as a possible comment. An experimental rig to show the feasibility of using the technology for autonomous vehicle communication. Yeah, I didn't actually explain that sufficiently. You see, the interest in this, which was sort of promoted by Sean Allen, and we should know about this, but the big thing in the modern world, and it's come upon us so quickly, is autonomous vehicles. And we'll perhaps be riding in vehicles where we have no engagement at all, or we're beginning to ride in vehicles where we do have engagement, but we're getting feeding from these antennae on information about road conditions and so on. And indeed, we even have instruments in our cars now which are telling us if there's a bad road coming up, maybe change the suspension, things like that. So one of the spurs to this use in vehicle detection and ranging was considering the significant amount of demand which will probably be there over the next 20 years or something, with the full introduction of autonomous vehicles. We thought the project would be exciting. Using the technology for autonomous vehicle communication could demonstrate this application while obviating the risk of the effects of long-term human exposure to transverse electromagnetic radiation. Okay. So I suppose what I've tried to do is I've tried to indicate to you that the theory is very sound, that Wesley's work is not, complete madness, that it's given rise to simple application of the equations which depart not very much from the classical equations of Maxwell and so on, but there are some modifications and extensions. But if you do that, you find that there's no reason why we don't have these scalar waves. And then I've given the classic experiment, which is done by this gentleman with whom we're still in communication in Switzerland, Christian Monstein, who worked with Wesley, who sort of introduced the theory in the first place. They got very promising results, and it's worth getting their paper, which I've given the reference to. Okay. And I've also given, I hope in fairness, some slightly more mainstream work, which is not just saying, don't read these papers, they're rubbish, but these people in Texas did the experiments and they basically got the same results, but nevertheless, they're interpreting them quite differently. So in fairness, one might want to look at their work as well. And I've already given the acknowledgements. As I say, this couldn't have been done without the significant input of the various people. I felt that I've been just a bit of a coordinator in all this. Denny's ideas, he was pushing me in the first place, and others, and we were doing the conference calls. And then my introduction to Jim Wolter, who's a very impressive man, actually. He's a can-do man, and he also is open-minded. He knows the theory. He's been trained well. And of course, we were very lucky to get in contact directly with Monstein and get his advice. And of course, this project, which was sort of, I won't say foisted upon us, but suggested to us by Sean Allen, looked very promising. We thought we were in for a winner, a big money spinner. Mind you, I don't know if I have 20 years to wait around to make my millions, but anyway, it looked like it was a project which could yield some practical value. Although I think, I speak for myself anyway, I was most interested in the theory. I'm delighted to have been able to share it with you, because these fortnightly sessions we've had a lot of interesting sessions, and maybe I'll just take the opportunity. I know I'm not hosting today, but with Franklin's permission, just to say that we're looking for volunteers all the time, and I think we have a number of talks for the future, but we're running out. We're running out maybe the second week of June. So if people would like to get in touch with me or Franklin, we'd like to talk about that. But I had a discussion with Jenny, and I said, maybe I should be keeping some of these things secret because the project could be run, and it hasn't been intellectually protected insofar as the longitudinal radiation part isn't. But then he said, no, go ahead, give the talk. I hope it has been of some benefit to you. I've just taken under the hour, so I'll hand back to Franklin now. And I have to do that myself because I actually have all the administrative controls, although I'm merely a talker today. So thank you very much, everybody, for your attention.
All right. Thank you very much, Ian. Ian, why don't you go ahead and put yourself up on the screen as well? I think I have some comments for you, some initial comments. So because I have a special interest in this longitudinal radiation thing. And so I thank you for actually finding the reference for the experiment showing that radio waves do appear to be longitudinal with that rotating set of rods there, So because I've been...
Well, just a slight caution there. Yes, I accept most of what you're saying, Franklin. But, well, the thesis is, whether you accept it or not, because I know you've done work in analyzing the longitudinal nature of electromagnetic radiation. But I think what we would say, or what I would say at present, is the normal radio waves which we're using all over the place are transverse. And you have these two components which contribute to the power density.
But I want to ask you, this is the critical question I keep on asking people, that if we believe that it is transverse, and you agree there is an electric field and a magnetic field, is that correct?
In the conventional case, yes. Not in the one I've been dealing with today, yes.
But now, even in the conventional case, this is what everyone believes, but are you aware of any experiment that individually detects the magnetic, say just the magnetic component? If we were to just say put a compass in the path of a traveling transverse wave, we would expect to see the compass oscillate like this. Similarly, if we were to just put in a very sensitive electric field sensor in the path of a radio wave, we would see it, do this. Now, I was explaining in the comments that an electric field is something which is a vector, and all a vector has is a direction, pointing direction, and a magnitude, how big it is, right? And so we should be able, and that's what is shown in the standard transverse wave picture. We see this, we see them alternating in 90-degree angles, but are you aware of any actual experiment that can actually measure the magnetic field just separately? Has it ever been demonstrated, I guess is my point, experimentally?
And actually, you've made this point before in our discussion, so I know it's a good point you've made. I would probably have to concede that I don't have any particular experiments to hand which I can supply to you. It could be looked into. But I possibly would say just off the cuff that the theory for the vector waves, if you like, rather than scalar waves, would indicate that there's the transverse nature of the E and H fields. So the onus would be on somebody to perform an experiment to show that they're not transverse. Example for what Manstein did for the longitudinal waves.
Well, let me just interrupt. I would say I would disagree. I mean, if you're putting forth a theory, it's your burden to confirm that theory. It's not my burden to disprove it. So, my point has always been, if everyone believes in transverse waves, that's great. It works out on the chalkboard, certainly. That's why everyone believes it, but not a speck of experimental evidence to directly support this idea that the light wave or radio wave travels as an alternating magnetic and then electric field. I mean, the theory is that you have the electric field, and as it decays, it generates a magnetic field, which as it decays, generates electric field. That's part of the extended form of Maxwell's equations, which I don't think have ever been experimentally verified either. I mean, that's my kind of my spiel on this topic, in that while you seem to think that the transverse wave still exists, I would go further, and I would say that no, the all radio
bring you in a second, Denny.
Really longitudinal. Because I also made this comment that I don't think the electric field is, say, compressible, which is something that you can apply wave mechanics to, because it's a vector field. Vector fields don't have any concept of compression.
I was going to say just one or two quick things. One was that although I don't have experiments to hand, I do suspect that they do exist, actually, Franklin. The second thing is, it appears that you are saying that these longitudinal waves that I've been talking about today, if they exist, are effectively no different from conventional vector waves, because they're all longitudinal. But let me bring Denny up, because I think he may have something to add. Denny.
Yeah, go ahead.
According to usual theory, if you take a red light, for example, emitted from a point like a little tiny red bulb, then the magnitude of the magnetic part of the wave and the magnitude of the electric part of the wave, there's a factor of the speed of light, which is 2 times 10 to the 8th. And the small n goes to the magnetic, and the large n goes to the electric. So the magnetic part is essentially almost negligible, as it were. Except it's not really negligible, of course, but it's so much smaller because you divide by the speed of light to get its magnitude.
Now, in what Ian was showing is that he was saying that the longitudinal wave basically has just the electric component. Is that right, Ian? Is that?
Yes, and I mean, I'd like your comment on that, Denny, because that's something I came to myself. I think in the early days we were talking about magnetic components as well, but then when I just went from first principles into the equations and found that actually the magnetic effects were not there, and it was merely the E field, which was in the same direction as the pointing vector, which is the energy flow field. That I said, well, then there's no magnetic thing, and it's incorrect to call them longitudinal electromagnetic waves. Now here we might differ a bit, because I said, well, certainly these waves are not electromagnetic; they're electrodynamic.
Well, they include an A field, which is, but it's just that the curl of the A is 0 in the case of longitudinal. But
right.
When you go from the A field to the B field by taking the curl of the A, you throw away a lot of information. It's not that there's no magnetic part of a longitudinal wave, but the magnetic part is a field part whose curl happens to vanish, which is B happens to vanish. So when you say there's no magnetic part, that's strictly speaking correct, but there is an A field part. It's just that the curl of the A field in that case vanishes.
Yeah, well, when you first drew that to my attention, it was a very important point. So I looked into it further, and I accepted your explanation, because I wasn't quite sure in the early days. So that is true. The A field is fundamental. And if you keep on using that, you will have all the information. So I suppose my language could have been a bit loose, but certainly the magnetic induction, the curl of the A disappears, but the A field is there all the time. Yes.
So in other words, you did some experiments, Franklin, and with the A field and the B field, and Ian and I pointed out that the A field from say a wire traveling along is in the same direction of the wire, whereas the B field curled a straight long wire. The A field is in the same direction, or in the opposite direction, one of it, I can't remember, to the current, while the B field circles the wire, and the circles move down the line with the current. So your experiments tend to indicate that the A field is the right way to look at things.
Well, I think that's a little bit different than what we were talking about. I mean, that's just around the local field of the magnetic field. And there's just this difference between what we call local field and then far field. So light and radio
field
waves,
and far field,
light and radio waves are a far field effect because they're supposed to be kind of self-propagating, so it can extend well beyond the source of the transmission. It's remarkable that my radio tower in downtown Seattle is like 50 miles away. And yet I can still receive it on my dinky little, 1 yard long antenna sticking on my roof. So that's an example of far field. So I'm not quite sure that, things like the near field B and A field, certainly we can measure those in the immediate vicinity of a transmitter. But my point is that when you get like 50 miles away, you stick like a Hall effect sensor, which can detect magnitude and vector direction of a magnetic field very accurately, and with enough frequency response that it could see the radio wave. And I was looking. I personally don't have one of these high-speed Hall effect sensors that I can just stick in the air, put it next to powerful radio transmitter, and show that there's no measurable oscillating magnetic field. But that is what I would predict, and the lack of anyone actually presenting any such experiment kind of goes against the fact that maybe it's not true, right?
Well, if you take Gell-Mann's advice, anything that's not forbidden must happen. Then that would argue against what you said. But I think what you said has some merit, and that you should remember, though, that the magnetic part of an electromagnetic wave is, compared to the electric part, you divide by C, which is huge, 2 times 10 to the 8. And so if there is a magnetic field, it might be awfully hard to detect.
See, also, if you consider just the longitudinal part, the part in green there, A doesn't appear there at all. It's only a function of the scalar potential. That's basically why they've been called scalar waves, I understand.
Yes, but in any case, we do have instruments which can't independently measure, say, the electric field. They're like electroscopes, and we have things that can precisely measure magnetic fields, Hall effect sensors. And even if the effect is small, if I go stick it right next to my commercial broadcasting antenna broadcasting at like 100,000 watts, I think you'd still be able to see it. Although I see we have some comments here. So we from Fractal Woman says, I think polarization is proof of transverse waves. Longitudinal waves can't be polarized. Can radio waves be polarized? And so what do you think of that comment, Ian?
Can longitudinal waves be polarized? Yeah. She's also talking about helix waves, but that could have both components. Yeah.
But me personally, I think polarization is proof of polarization. It isn't evidence of, say, of the nature of the wave, that it must be transverse. Because the way that polarization works is that you have an antenna, and like this is a rod antenna and this is a rod antenna. And the thing is, the way polarization works is that if they're both aligned in the same direction, then you get maximum transmission. But if it's at 90 degrees, then you get minimum transmission, right? So that's the actual experimental reality of polarization. But now, does that really tell you that the waves that came out of this thing, that they had to be transverse versus longitudinal? And I would say no, because if you were to imagine this transmitter as putting out a wave the same shape as this pen, which would be a cylinder that is expanding out as a longitudinal way, right? And it's more compressed and more spread out as it reaches this receiver. And when it receives it as a cylinder, that is going to impact this cylinder the maximum. Like the entire surface of the cylinder is going to be impacted by the wave. It's literally like this pen hitting this pen. And so, but if I put it this way, if I put the transmitter this way, then only a tiny fraction is going to actually intercept the pen versus the entire surface area. So, to Fractal's Lumen comment is like, does polarization prove that the wave is transverse? And I say no, because a longitudinal wave can also explain polarization. So, but people do, equate polarization with transverse transmission. So.
Well, I think I would as well. So we probably differ there. But I also conceive that the experiment they did, Munson and Wesley, with this polarizer analyzer, indicated that the power transmission was in one direction. It wasn't transverse to that. But I do conceive that you could have a longitudinal wave which was not confined to one plane. And if you confined it to one plane moving forward, then it would be polarized.
Yeah, but I think that's another important thing, is that waves aren't constrained to a single plane, like this piece of paper, right? That's a single plane, and what is typically drawn is like a sine wave on the plane. But radio transmitters are not in one plane. They look like this. There have to be physical things like a rod antenna, or it may be shaped in the shape of like a UHA loop, or in the case of the experiments that Monstein did, in the shape of a ball. Right now, the thing with a ball is that a ball should send out completely non-polarized waves, because it doesn't have any particular direction for a wave front to be created, right? So that is interesting about what you said about the ball transmitter, and that they were using that to transmit their longitudinal waves. But I think maybe what they were doing was that they were merely transmitting a radio signal which has no polarization. And so once you have no polarization, it's not like a rod where you put the other rod in the same orientation. In a ball, it's like the rod would receive the signal the same no matter which orientation it is, because it doesn't have any particular orientation. But so if you eliminate the effect of normal polarization, then you can use an array like you showed on the chair to show that even though there is no polarization, that there's still a preferred way to receive the signal, which you could compare against versus if the medium was going up and down, which is, well, that's another problem, and that the medium, the transverse component of the waves theoretically isn't actually something going up and down. It's actually the electric field going this way and that. It's switching direction. But even if you did think it was going up and down, then you could theoretically predict if I have a rod antenna and if the wave's going this way, that it's not, you're not going to receive anything. But if it's going this way, you're going to receive something depending on, how the rod is oriented. But
well, yeah, and the difficulty, of course, was in their analysis. They were detecting the transfer of energy, but you're asking about the transfer of the fields, and
that's the thing, is that all we get on in the experiment is the transfer of energy. All we can do is measure the voltage, and it is presumed that with the standard transverse electromagnetic wave picture, that it's induction that's doing it, right? You have a magnetic induction, varying magnetic field directly inducts into the antenna, and that's why we see the voltage. Or they also simultaneously say that we have the electric field changing, and the superposition of the electric field upon the receiving element also generates electricity. So there's actually two things that could generate electricity in that view. But my feeling is that that the radio wave is just like sound waves, and that you just have a medium like air, and the transmission method is purely by compression and rarefication. And when you receive those longitudinal waves, they're just literally impacting the surface of the receiving antenna, and that is what is causing the voltage, not any form of induction, no magnetic field, no electric field. Is literally you're pushing against the surface of the receiving antenna, and that's what's causing the voltage, right? So that's a completely different way of looking at why would it be a longitudinal wave. I mean, you presented a lot of math, kind of saying that you're still trying to save the electric field, say, and just represent that as the longitudinal field. Although other dissidents go the opposite way, and they say that there's no electric field, that there's just magnetic field. They want to make it so that's all magnetic. But really, you could have picked either one, because I don't think either one actually exists. What only exists is that we know that there's a wave, that when there's something where it has a high potential and something has a low potential, there's definitely, a wave. And, that's just my opinion, that I prefer to say that, yeah, it's a longitudinal wave. It's always been a longitudinal wave. And it's just a wave in a medium, right? That's kind of my deal. It's like, once again, I am puzzled. Why is it people believe in the transverse picture when there is no direct experimental evidence showing it?
Well, as I say, that would be another investigation. But my own view is that it's totally consistent with all the theories. We know. You're running a bit in the face of that, if I may say so, frankly.
Well, the thing is that those are all equations on chalkboards, right? So, do we believe scientific theory, which is based entirely on chalkboard calculations? This is like string theory, right? It's like you've got all these equations. If you have 8 dimensions or 10 dimensions or as many dimensions as you need, works out fine on a chalkboard. Not a single scrap of experimental evidence to support it. I mean, is that good science, do you think, that we just...
If there were no experimental evidence to support all this mathematics, you're right. You are right. But I say it is consistent. We do have a lot. And actually, I still would say that we could get some experimental evidence which would indicate that you could measure the electric field and the magnetic field. It seems such a consistent type of theory with all the other experiments we've been done. That perhaps is something for another day, but that would be my own. Because I did initially think that you were saying that what I was proposing was no different from ordinary waves, because they're all like that. But you're not actually. You're making them even more fundamentally the same as sound waves or mechanical waves.
Now, who do we else have in the green room? We should bring up some.
Yeah, okay, good question, because I was doing the comments. We have a couple more. We have Bob Gray, whom I had a brief conversation with just first. We have James Keane and we have Eric Reiter. Would you like me to add Bob to the stream, because I think he may have some comments.
Yes, let's add Bob. Let's see what he's got to say.
There's no video though, Bob. You have to unmute yourself. Oh, there is now.
No video.
Got it now.
Hi, guys. I'm not really sure what to say at this point. I did think I saw some references about the biological effects of longitudinal electrodynamics on living organisms. But I just checked again now, and I couldn't find them. But I'd like to see that, because I'd be interested in understanding what the antennas is shape and how it's fed. How do you feed those special antennas for longitudinal waves? That would interest me an awful lot, because I can't imagine they're the spherical shell with the feed up the middle kind of antennas. So what antennas are used to generate longitudinal and a very small, circuit board size, which I would assume you would use or want to get to for the autonomous vehicle, drones, or any other, things. You wouldn't want to mount a big sphere on anything like that.
Too big, yeah.
Yeah. So I don't know, Ian, have you come across references specifically on longitudinal antenna designs?
Yeah, just a couple of things, Bob. Just one thing, just a bit tangential, is I mea culpa. I made a mistake. It was actually Dennis's other son, Pat, who was working for the Minnesota Department of Transport, not Sean. So I think we had some help from him as well. So that was an error in my my description. But we were thinking about that, and I think some of the original calculations gave this too large antenna. And then we looked at what Monstein and Wesley had done, and we said, well, we'll try maybe to restrict ourselves to them. And then I started playing around with what would happen at resonance frequency and so on. And I got these more reasonable values, which were sort of like maybe diameter of a meter or something like that. But you just shortly before the presentation, Bob, kindly supplied me with a reference where, this was of some interest. But it might be worth your while having a look at the original Monstein and Wesley paper, because it didn't cover everything in it.
I've read that many times, actually.
Okay.
But some years ago now. I'm concerned with their design. I'm not so concerned with their experimental results. I think their experimental results are good. But I'm concerned with that center feed design, because that center feed, I would think, would act like a normal antenna. And I'm not, because it's a straight wire and it's oscillating. Isn't that a regular
there though?
Over it.
Yeah,
but how do you feed?
Transmitter.
How do you feed that? Feed it this way and then it comes up to the sphere, or is it all a straight and only the tip of that is covered, so there's still a straight part?
I think you had a picture of that, Ian, right? It was just
It just concerns.
I just took that from the paper.
Yeah, it just concerns me. As I say, what the moving forward in the future and for applications, what kind of designs for an antenna would be. So
I bring Denny in again, because I think he may have an answer to that. Denny.
The Monstein-Wesley experiment showed, according to some people I can't mention, showed that yes, there's two types of waves coming. But the type that Bob just described, the straight wire coaxial cable to the center, does give off transverse waves. At the same time, however, the fact that the charge goes shielded or insulated to the center, does cause spherical waves too, and those too have been detected. And so part of Einstein and Wesley don't mention this. Well, Wesley basically wrote it. But yeah, there are two types of waves being emitted from that antenna. And this has been, there's detection of this, and I wish I could go into more details, but I can't. But Bob is quite correct. There are the fact that you got the center feed to the center, there are going to be transverse waves coming off, but at the same time, there are also going to be longitudinal radiation, and both were really measured, I guess.
Good. That's all at the moment. Thanks.
Thank you very much, Bob.
You're welcome.
Who else do we have in the green room today?
Okay, so I've just sending a comment to Jim Morrison, but we have James Keane and we have Eric Reiter. Shall I put James up?
Well, we do have a question from Jim Marson. So how is it different from the Poynting vector?
Well, I've answered that.
The vector is just the expression of the energy transmitted by a radio wave, right?
Well, I just said it's not different, but there are just different expressions for the Poynting vector for the both types of radiation. I don't know if that answers Jim's point, but it still is based on the same.
Wesley,
Denny,
I lost my train of thought. I'm sorry.
Yeah, we're talking about whether the Poynting vector is just another.
The Poynting vector. Yeah, the Poynting vector, according to Wesley's scientific physics, is a special case of what's actually going on. And the general so-called, you might call it a Poynting vector, but Poynting only did it for Maxwell's equation type wave. The Poynting vector is just like the Lorentz law of force, is a special case of a more general result. And it's in chapter 4, I think, of Wesley's scientific physics that he talks about that. Let me quickly look that up. I think that's chapter 4. He goes into that. Yeah, 5 is induction, 4 is electrodynamics, and then section 4.23, longitudinal electrodynamic waves, and 421, the transverse magnetic wave, 422, electromagnetic wave, and so in that part of his book, he goes over all this. And he also earlier he points out that the Lorentz law of force does not conserve energy in the general case, and so cannot be right as it stands, but it's part of a more general law.
Yeah, he talks about that and the Biot-Savart law as being particular cases which in general will not satisfy the energy conservation nor comply with Newton's third law.
Well, I'm just a little bit concerned that, the Poynting vector just expresses the, say, the net energy, which means that, from a receiving antenna standpoint, that's exactly what we see. We just see the net energy that goes across. And when you look at that energy, which eventually just, if you put it on an oscilloscope, it could easily be from a longitudinal source, right? At that point, you can't tell, right? All you know is you've got a wave, which has variable magnitude, right? And that's,
I suppose that's true once the energy is received.
Yes. Energy is, and but that doesn't really tell you, how it got there, I would say. Because I think, so Harry has this interesting question is, how do you know there are different waves, because I think that's what Bob was concerned about. Is like, how does this uniquely transmit just longitudinal waves versus transverse waves? That I think Harry is asking is, how do you even know that there are different waves and not just different wave modes, I guess.
Well, as Ian pointed out, you have a 3x3 array of rods that are half wavelength, and if you turn them one way, which would allow transverse waves to propagate, you get nothing. If you turn them the other way, which would interfere with longitudinal radiation, well, I think I got it back. Anyway, go ahead, Ian. I think I've got 2 minutes left.
That's right. I mean, these polarizer, analyzer elements would indicate that, when they're at 90 degrees to the direction of travel, they have no effect, and when they're in the direction, they have maximum effect in reduction. Isn't that the case?
This indicates longitudinal radiation is the only type of radiation that have that behavior.
But by the way, Franklin, Harry has joined the green room. If you want him to be brought up.
Yeah, if Harry would like to come up, I'm sure he's the radio expert. So
yeah, exactly. Okay, well,
if anybody needs to know, it would be Harry.
And I'll bring Harry up. Harry, good morning to you.
All right. My comment is, I don't think there's enough detail in the polarizer array, as it's called. To me, there's not enough detailed description in how the experiment was conducted. I agree with Bob Gray. I don't see how the antenna could radiate. So I think, until, you can tell me more about how the experiment was conducted, I just don't see this as convincing. That's kind of my comment. And, how does this antenna work? I agree. I don't see how this antenna works. You should have presented more information about that, Ian, I think. That would be my comment.
That it works.
There, knowing what I know about radio, there's all kinds of phenomena that could happen. You can have, dual reflections off of objects that could make it appear, ground reflections. Was this done in an anechoic chamber? Certainly not done in an anechoic chamber, because it wasn't, they didn't spend a lot of money on it. So, there's a lot of things, a lot of questions.
Yeah,
the experiment was done in the open air, actually.
Yeah, I have a link to the Butterworth paper where they, like Ian says, they replicated exactly Monstein-Wellesley's result. But of course, as you say, that is still like way open to interpretation, because at the end of the day, on any antenna, all we're going to be able to measure is the voltage that comes out of it, right? And
power is what's measured that comes out of the antenna, Franklin, not voltage.
Well, what goes into the
voltage is a manifestation of the power that is received by the antenna.
Yes, that's absolutely right. But that's the only thing that we can measure.
Well, power can be measured.
Yeah, well, that's part of the voltage, but if you're interested in getting the details, I'm sure all the details are in that paper. I myself, I'm going to immediately go and delve into that paper and see exactly how they did this, because this is kind of a lost result to me.
Well, Ian, here's my comment. My question would be, what is the objection that Butterworth and those people, what is their objection? Do they have an experimental objection? Do they have a theoretical objection?
It's a very good point, and I was just thinking of that, Harry. I probably should have done a slide on that. So I might have to refresh my mind if you just give me a moment on that.
Now, curiously enough, I couldn't find an actual reference to the original Monstein-Wesley paper. Maybe it's in there in the references, but I just couldn't find an immediate.
You mean my references? I gave it in my references.
Oh, okay. You may have given it in your references, but I was just looking for a quick internet link that I could post.
Right.
But we do have the better.
Yeah, I'm just getting up my original
paper.
See now what I have here. No, that's not it. It's another one here. Here it is. Yeah, they seem to go through the whole thing.
I mean, you can read the abstract, and it says our experimental results actually resemble MW's theoretical pattern more closely than did our own experiment. An interesting result, considering that MW's theory is almost universally considered incorrect. So that's interesting. Of that,
Yes.
That MW's theory more closely matched than their own theory. However, our experimental results were not compatible with Ryblicka's very plausible theoretical explanation. So I'm not quite sure what to make about that. Thus, we dispute MW's claim on theoretical grounds and Replica's ground plasma currents on experimental grounds. So they're disputing both of those on experimental grounds. We conclude that an unidentified mechanism must be producing the observed results.
She's kicking a bit
to the results. They're saying that must be something unexplained.
That's right.
Which is kind of a weird.
And let's go back to the slide where you show the polarizer on the table.
Yeah.
Rotating on the chair. I don't understand how that thing. Okay, I have no idea what that is. Okay, I have no idea what that's. Okay, a lot of antennas look like this. Now, my question is, what does it mean? What does it mean? How is he getting a null? In what direction is there a null?
These are rods which are put in the path of the supposed waves. And when the rods are put at right angles to it.
Yeah, that makes it into an antenna, basically. That makes it an antenna. A stacked antenna array. That's what we call what you have there is a stacked antenna array. Okay, you got like three antennas stacked on top of each other. Okay, so in what direction do you get a null, and how are they rods connected together? We don't know.
How are the rods connected together? Well, see, my understanding.
I don't understand. I don't understand this. All right, I'm sorry, we have a delay. I don't understand this experimental apparatus. That's my point.
Right. Well, my understanding, and Denny may be able to come in here, is that
in what direction?
When these rods are in the same direction as the supposed longitudinal radiation, they would act to what's the word? Not absorb them, but to attenuate them, and therefore.
Okay, Ian. Are the ends of the rods pointing towards, or are the sides of the long sides of the rods pointing towards the antenna? That's what I don't understand. What's this angle 0? What is 0 relative to?
Well, you have the two antennas here.
I mean, where is 0 in this? Where does 0 It says 0 deflection angle. What's the reference angle of the apparatus on the left-hand side?
So
I don't understand that part.
If you draw a straight line between the transmission antenna and the reception antenna, and then you put this apparatus in between, and you turn the table, and then you measure the angle between that straight line and these rods, these lambda/2 rods. That's my understanding of what that angle is.
Yeah, I would guess that like what is shown in the picture there, like you would put the spherical transmitter to the left of that, and say the angle that it's currently showing is perhaps 0, or it's the opposite of that. It's one of the, so, and then when you rotate it 90 degrees so that the antenna are now facing the spherical transmitter, then perhaps that is when you get the maximum. So it's going to be, one or the other. I don't know, as a radio transmitter expert, Harry, what you would predict. But my objection here is that, well, you could have put any radio transmitter to the left of that thing, and you would get polarization, right? I think that's pretty obvious, right? You could put a stick transmitter there. And,
I don't understand the experiment. Could you describe it again? Is there a receiver? Is this device placed in front of the receiver antenna, or is device that's on this rotating chair, is that the receiving antenna?
Yeah,
no.
No, that is the receiving antenna.
Harry, this is placed somewhere. Probably doesn't matter exactly
Okay,
where.
All right. I have to confess, I don't really understand this experiment. And I've seen this paper before. I've looked over this paper before, and I never really understood this whole Monstein paper. I couldn't really understand it. And unless there's I'm just confused.
Well, Harry, let me just ask you as a radio engineer. So suppose that thing, that's the receiver, right? And it's all connected together, right? And it has one output, right? And you stick any transmitter you want to the left of it. So as you rotate that transmitter around, what would you expect?
I don't know what this device is. This
It's
thing with a bunch of sticking out of it.
Well, I don't know why you don't.
Depends on how these rods are connected together. They have to be connected.
Just presume they're all connected together, Harry.
And the other thing is, I don't know where the device that's detecting the signal is located. So if it's just a bunch of rods stuck into a board,
yeah, they just presume that the rods are all connected like a TV antenna, and there's a wire going down the center of the board that is connected to, I don't know, like an oscilloscope or something. So if that were the case, that's what I'm asking you. So let's just.
I don't know. I don't understand what they did.
The measurement is made at the receiving antenna. That's where the oscilloscope is connected, not to this unit. This unit is put in between, and depending upon its rotation, you're seeing how the receptional signal changes.
Okay, so this is a polarized. This is a filter. It's claimed to be a polarizing filter.
But Harry, I hope this isn't too much of a cop-out, but it's an offer. Like, if you had a couple of prime questions on this paper, which we could answer, I'd be very happy to forward them to Monstein.
One path for the signal.
I'd be very happy to get any direct answer from Monstein about anything that we can't answer. I'm sure he would do that.
Well, if this is I mean, as you said, Ian, this could be a polarizer between the transmitter and the receiving antenna, in which case we need to know what the receiving antenna looks like as well. So, but what do you think of that, Harry? It's just a polarizer, like a polarizing sheet you stick between the transmitter and the receiver, and somehow it just absorbs what's in the middle. Does that help?
Well, that's I guess mine would be does Butter description of the experiment in their paper, And obviously, an obvious issue would be Butterworth or et al. Understand how the experiment was done by Monstein and Wesley, and how well. So if you don't understand how the experiment was originally done and are able to reproduce it based on a clear understanding of how it was done, then I could see where you may or may not get the same results or not get the same results. I mean, it's.
Well, they don't admit to that. They don't seem to have any problem. They're talking about they wrote.
Well, I think the bottom line is we're not really sure how this experiment was done. I mean, I don't understand how the antenna works, the spherical antenna. I don't understand how that's supposed to work. I have Bob Gray's observations about that. And I don't understand this polarizer. And I guess it's just basically rods mounted on a board. And then there's an antenna behind that polarizer that detects the signal. And as they rotate that polarizer, the signal strength goes up and down. That's my understanding of the experiment. Now, that might be valid if you only have, depending upon what wave reflections, you could have wave reflections from the ground or nearby objects that could mess up your results. So you have to eliminate those.
Well, I think it's worth reading their paper. Unfortunately, their paper doesn't have any photographs of the experimental setup. But they seem to be intimately.
Yeah, I've read the paper before, and I didn't understand it.
See, Butterworth et al. Dispute the theoretical basis to this in the first place. That's basically what they're saying quite clearly here.
So they did an experiment which they think reproduced the Monstein-Wesley experiment. They did an experiment which they think reproduced it and got somewhat similar results. And so then they couldn't say, well, it's wrong because we proved it by experiment that their experiment's wrong. So they just said it's wrong because of the theory.
Yes, I think that's effectively what they're saying.
Yeah, effectively, that's what they said. They said they still disagree with the theory.
But we can't understand how the experiment was done in the. Maybe they have a better. I haven't read the Butterworth paper. I have read the Monstein paper, and I looked at his antenna, and I didn't understand it. I'll be honest about that.
Well, I guess that's why we had the discussions to, Harry, go back and take a look at the Monstein, look at the Butterworth paper, and, you can decide for yourself whether he showed that the radio wave has a longitudinal physicality, I guess. Although I think it's funny just to even talk of longitudinal.
Well,
because, that implies a compression rarefication thing versus field theory, which only deals with scalar quantities, right? I mean, what do you think of that, Harry? It's like a magnetic and electric fields are described by scalars, which only have a vector direction and a magnitude, right? There's no conception of say compressibility. There's no well, not unless you, I don't know. I guess you could maybe think the magnitude was the same as compression, but generally speaking, we don't talk about taking an electric field and compressing it.
I could spend a whole lot of time on this as a radio engineer studying all this, and then you could spend a whole lot of time and money reproducing the experiment and going out in the field and not really understanding, maybe reproduce what they did. And I mean, it's just
kind of breaking up there, Harry.
Breaking up a bit there. Yeah.
Okay, I guess I'm off the air.
can hear you now.
it's,
You're
we've
kind of
got
breaking up.
problems with the delays. Yeah, my point is, this is one would need a very detailed description of this experiment and how it was done in order to really understand what's going on here. I don't.
So Robert K has an interesting comment. If you were to measure a longitudinal wave, what would you measure about the wave besides frequency and wavelength and intensity? It's like that's all the things you can measure, right?
Those would be the main parameters, certainly. Yes.
But the thing is that if it was a transverse wave, you'd measure exactly those three same things, right?
You would indeed, but in the interim,
Well,
you might be looking at the magnetic component and vis-a-vis the electric component, which you wouldn't be in the longitudinal case.
If I might interrupt here for a minute, the whole theory of electricity is that if you have a longitudinal electric wave and not any magnetic field associated with it, then you cannot transfer any power. So therefore, no signal will be received at all, period. So to me, there's a problem there. And what you're saying, something about the pointing vector. I mean, the pointing vector is a measure of the power, not energy, because energy is static. It doesn't move. Power is what moves. So power is moving through space. That's described by the pointing vector. Okay. So in order for an antenna to pick up power from a excuse me?
Why do you say that's zero in the case of the longitudinal wave?
Well, the assumption is see, this is where, I mean, I'm kind of confused about the theoretical description, because to me, you seem to be sort of saying that the pointing vector behaves as if it's a longitudinal wave.
I mean, I think it's interesting, Harry.
Is
you
that
say
correct,
that,
or am I
mean, you're saying that if you just had an electrical field source, like you had like a Van de Graaff generator, all you did was turn it up and down. So, you generate variable electric field. But if you put an antenna some distance away, that just the varying electric field is not going to transmit any power. Right? Is that what you're saying?
Correct. You can't transmit power with a static electric field. It's doing nothing. It's static.
Yeah. So, I mean, that's kind of, I don't know, maybe what Butterworth has got. It's like, we know it can't do that. So that's what I think in their abstract, you're saying there may be some other unknown mechanism that the power is being transmitted by if it can't be electric.
Here's you for what it's worth. You've got an antenna that's spherical antenna is going to generate.
Breaking up. You're breaking up.
But Cornelius also asked, a very relevant question: is the receiving antenna in the near field of the transmitting antenna?
So well, anyway, okay. So the bottom line is the transmitting antenna has numerous modes that it can transmit in. So the question is, what mode is being transmitted? What wave mode is being transmitted? That's really what the issue is. And it's not clear to me what this experiment is demonstrating, because there's just too many unknowns. But I'm just kind of, I don't know. That's kind of my view of it.
Danny may have something, I think, to say on that.
Well, Harry, if you consider an aluminum ball, say not just a shell, but a ball, and you assume that at this exact center, electricity is being fed somehow as a sine wave, say. And so then the electrons are going out towards the periphery of the cylinder in a spherical symmetry, and then in the other part, they're coming back again. So you have center-fed aluminum tin. We're not saying how, where electricity is, current is going in and out.
Okay, well,
Just a minute, I got it. And then if you try to compute the magnetic field, it's zero. So all you can have is the electric field by symmetry. Now, the fact that you have to center feed it somehow means that there will be also transverse waves. But if you just take the model of an aluminum cylinder with electricity being fed in and out as a sine wave into the center, you get electric waves be emitted from the surface of the aluminum ball, and they go out as longitudinal radiation, which is not connected with the A field, like I said before. That was a mistake. I got mixed up. So that's why the antenna generates some, at least, longitudinal radiation, because this spherical symmetry, which rules out, if you look at the equations, rules out any magnetic field. Now, as for the polarizing thing on the chair, if the rods which are half wavelength, are in line between the line in the center of the receiving antenna, which is same as the center, which the receiving antenna is just that ball that with the center feed, and the transmitting antenna is the same thing, same size and everything. Then if you draw a straight line between the center of the two end spheres, the transmitting antenna and receiving antenna, if the rods are in parallel with between the line joining the two centers in parallel, then the longitudinal radiation will be damped by the rods. There'll be current induced in the rods, which will be consumed by ohmic losses, so that the signal would be at a minimum. Whereas if you turn the 9 rods perpendicular to the line between the two centers of the two antennas, one a receiver and one a transmitter, then you would expect little or no damping to occur. So that's the idea. And now you're making the point is, well, what if these waves are reflecting off something and so on? Yes, that's right. They should have done more. But the basic idea is quite simple. It's just a matter of spherical symmetry.
All right. Well, thank you for that explanation. I think, Denny, you looked at that a little bit closely. And although it seems that you still have to make a bunch of assumptions about how the radio wave is interacting with the rod. And, but
the wave goes out as almost a plane wave in a sense, except it's curved, but because it's from a sphere. But the electrical vectors are parallel to the rods, and hence they set up a current in the rods. And that current is consumed by ohmic losses. So the power drops way down when the rods are parallel to the line between the two centers of the two antennas, one a receiver and one a transmitter.
So you're saying when the rods are pointed right at the transmitter, that is when you get minimal transmission?
Yeah, because the electric waves going out from the transmitting sphere are basically parallel to the rods, and the rods are half a wavelength. So you get it dampens the signal.
Dampen, yeah.
Go ahead, Ian.
No, dampen was the right word, and you'd actually put that in the comment. That's correct.
Yeah,
Vinny.
yeah. Harry, do you understand that?
Yeah, well, he's not on right now. I don't know if you want to bring him back. Although we are getting short on time, so we have
Oh,
5
yeah.
more minutes left in the conference. I wondered if anyone else in the green room, we can bring them up.
If they wave, I can see them and alert you to them, Franklin.
Yeah, we got anybody waving?
No, nobody's waving at the moment.
No. Although I kind of feel like if you're in the green room, you've already volunteered to speak. So.
Well, wait, I think Jim has changed his mind.
Okay, bring up Jim. See what he got to say.
He's up now.
I'm thinking of the Eric Reiter work where what if, for example, instead of using 443 megahertz, you had a single pulse in your spherical transmitter? If there's a longitudinal wave, there must be something going on at the receiver which has a duration greater than that single pulse. Does that question make any sense to anybody?
Well, I mean, that's an interesting question. See, I'm thinking that, okay, you send a pulse. Now, the controversy is to whether it's sending out a transverse wave or whether it's sending out a longitudinal wave.
If it's a longitudinal wave, you should presumably be able to record events occurring after the conclusion of the transmitting event. Think of, for example, an explosion in water. That's a discrete event, but their waves can be set up lasting hours or even days after that single event. That's all I'm saying.
Well, I think you'd get that no matter which way the wave was transmitted. Unfortunately, that seems to be the main problem with.
Well, wouldn't that be the definition of a longitudinal wave? A wave that has a duration greater than the triggering event.
Well, I don't know why. I mean, even if it was a transverse wave, it would also last longer than the initial pulse.
Okay.
There's, in that way, I don't know that. And I think this is the main problem here is, claiming that it's longitudinal. But the only thing that we can get is what's on the receiving end, which just looks like a sine wave. It would be either type of wave, you would still get that. So the question is, what is the polarizer in between showing you? And I don't know. So, but we got a few minutes left. So I'm going to let Ian, Ian, why don't you go ahead and summarize what we've been discussing and close us out here.
Well, all right. Thank you very, very much. And my apologies once again for the lack of voice. I hope it doesn't ruin too much anybody subsequent listening to it in the recording. But anyway, what we did is we looked at the theoretical basis to this, which was first sort of adumbrated by J.P. Wesley. And his ideas are quite heterodox, really, but he was a very significant theoretician. And we worked on the base of that, and then we went a bit further. And then we saw the apparent experimental justification, which Monstein and he had done in Switzerland some years ago. So on the basis of that, and maybe Gelman's ideas, we said, oh, let's go ahead, we'd go for it. we worked a bit further, and we got a theoretical contractor engaged in the work, and then we were in touch with the Ministry of Transport in Michigan, and we looked at the possibility of applying this and so on. And we knew a lot more work would have to be done to quantify it precisely. And then, of course, the paper from Butterworth was come across, and it's very odd. I don't want to be prejudiced on that, because we're not we're not discussing that per se. But it seemed to me that they were trying to find ad hoc reasons to get out of it. You know, that they got the results, but they didn't accept them, and then they even say, "Oh, he didn't do proper statistical analysis and all that." So, so perhaps it's up in the air. I mean, as I said earlier, that we have had excellent responses from Monstein. That probably actually encouraged us to go on for a couple of years. And if Harry had any specific problems with, interpretation, we could perhaps put them to Christian, and I think we'd get an answer. I don't know if we've convinced anybody of the usefulness of continuing with these experiments, but for my part, I don't really have experimental facilities now, but I certainly have the time to indulge in theoretical speculations, and I'll be pursuing this a bit further, having been given the germs of it from Denny. I hope it was of some interest. I hope we didn't bore you too much. I hope we gave you enough mathematics to say the mathematics is there. You can accept it or you needn't accept it, but this is what it's based upon. And if there is a new form of or this form of radiation which hasn't been recognized, it's quite a significant event. I see one or two of the comments which we didn't have time to put up were in connection with maybe parallels with Tesla's works. So maybe original work of Tesla, he was looking at scalar waves as well, and maybe we're at the threshold of some new adventure, or maybe it's just fiddling around with mathematics, which leads nowhere. But anyway, I hope it's been of interest, and I hope my lack of voice, some of you might be glad of that. I talk too much sometimes, but my lack of voice didn't lead to such a bad articulation. I've made all the acknowledgements. Thank you very much, all of you, for attending, and thank you for Franklin for agreeing at short notice, actually, to come in and moderate this for us, because I think it makes a more structured debate. So thank you again, everybody. Again, apologies if I didn't talk as much as I should have. So you're going to close it, Franklin?
Yes, so we're all done, and since you are still our host, you'll need to stop the recording.